Okay, so welcome to the last lecture of the semester. You made it this far. Good job. So the exam review is going to be Friday morning, 9 to 11 a.m. here. I use lecture capture. Exam is going to be Wednesday next week, 10:30 a.m. in Math 100. The chapter 10 sapling, we finished that chapter on Monday, so the homework is going to be due 1 week after, 9 a.m. next Monday. And then the chapter 11 sapling, I've shuffled it around and swapped out some problems to sort of match the coverage that we're going to be doing. So it is still going to count as a homework set, and it's going to be due right at the start of the final exam, so 10:30 a.m. on Wednesday. Okay, so I've narrowed it down, the things that I think are most important from this chapter. We are going to be covering how to make ethers with the Williamson ether synthesis. We're going to cover making epoxides real briefly. And then we're going to cover a lot more of epoxide reactions on pages 5 through 6. So this is kind of the parts of the chapter you need to know. Everything else, if you're curious, it's in there, but it's probably less important than this stuff. Okay, so any questions about that? Okay, cool. So let's get right into it. Chapter 11. Okay, so we're looking at ethers and epoxides in this chapter. As a reminder, ethers are anything with two alkyl groups stuck on either side of an oxygen. And epoxides are technically a subset of ethers where they have this three-membered ring. They're one example of a cyclic ether. And it's a three-membered ring with two carbons and an oxygen. And then you can have up to 4 other R groups coming off of there, although some of those might also be H's. Okay, so ethers, we've actually already seen how to make them. We just haven't specifically looked at it in the context of we are doing this because we want an ether. So making ethers, there's a few different ways you can do it that we've actually already seen in other contexts. Like, for example, halo ether formation technically makes an ether. But the most common and generally applicable way of doing it is Williamson ether synthesis. Okay, so this is kind of a fancy way of just saying SN2 using an alkoxide. That's literally all there is to it. There's a few sort of things to pay attention to in terms of how you set it up, because it is SN2. Whatever you're doing SN2 on obviously has to be like methyl primary, maybe secondary. But we pretty much already looked at this reaction in chapter 9. Okay, so I guess actually there is one other part to it, and that is you got to make the alkoxide first, which we already saw how to do in the last chapter. So one way to look at it from the alcohol starting materials point of view is we take the alcohol, we convert it to the alkoxide using sodium hydride. If you remember from chapter 10, that was sort of a really good way of converting alcohols, ROH, into RO minus, because this deprotonates it, doesn't leave any side products around. And then we're going to bring in some kind of different R group attached to a halogen. That's the thing that gets SN2 done to it. And this way we can end up with an ether with two different R groups, pretty much freely chosen by us, stuck on either side of an oxygen. So whatever R prime is must be either methyl primary, secondary, and it can't be something that blocks SN2, so like no neopentyl. Okay, so quick look at the mechanism here. If you take sodium hydride, if you remember hydride is an H minus, that's going to come deprotonate the H, kick that off, give you the alkoxide here plus H2 gas, which leaves immediately so you don't have to pay attention to it. And then whatever our R prime is just going to come do SN2 on it. So we just get the SN2 product that way. So nothing really new here. It's just like learning how to use it to target the ethers that we want. There's a little bit of planning that has to go on here. Okay, so any questions about this before I do a couple of examples? Okay, cool. So say we want to make this molecule. So that's an ether with a T-butyl group on one side and a methyl on the other. We could sort of put this together one of two ways, hypothetically. In one case, we could do our little cut here line on that side of the oxygen. So in that case, we would have made it from this alcohol and this alkyl halide. You can use any halogen on here, but remember that iodine is the easiest to have SN2 happen to it, so we may as well like make this reaction as easy as we can and use iodine there. Okay, so that's one possibility. The other is if we cut on that side, then we could have made it from that alkyl halide and that alcohol. Okay, so top or bottom, which one of these routes is going to work better? Which one of these is asking you to do SN2 on something that's not really SN2 capable? Yep, the bottom one. Yeah. So if we tried doing Williamson here, that's not going to work. We're trying to do SN2 on a tertiary alkyl halide. So that option is not viable for Williamson. But this top one looks like it would work great. You deprotonate the oxygen, you come around and do SN2. This is like the perfect ideal SN2 substrate. and everything would work pretty great there. So in other words, you could just write this as this step 1 sodium hydride, step 2 methyl iodide, and that would get us the ether that we want. Okay, so pretty much as long as at least one side is SN2 capable, Williamson's going to work great, which is almost all of the time. So those will be the only cases I'll ask about on the exam, is cases where Williamson will work on at least one side. There are workarounds if neither side is SN2 capable, but I'm not going to cover those reactions because they're less commonly used. Okay, so questions about this? Okay, cool. So that was fast. Okay. So next up from this chapter is, we'll go over here. Yeah, I'm ripping through the first couple topics that I listed up there because they're pretty short, but the third part, epoxide reactions, I'm going to spend a lot longer on. Okay. Okay, so that's how we make ethers over there, guys. So how do we make epoxides? So again, there's a couple different options. I'm only going to cover the most commonly used one, just in the interest of time. Okay, so I guess you can sort of think of this as like you're trying to make a three-membered ring. We already know that's kind of unstable and high energy. So just kind of like making a cyclopropane ring when we had to resort to something kind of like a special reagent like Simmons-Smith cyclopropanation or carbines. We're going to have to use something special here too. Okay, so what we're going to use most of the time, and what you'll actually use for the first experiment in OChem 2 lab if you take that next semester, is a peroxy acid. So in general, what that looks like is, so a carboxylic acid is just CO double bond O and then an H at the end. Peroxy acid is the same thing with an extra oxygen in there. So COOH after the carbonyl, or RCO3H, you might also see it written as. Okay, so there's a couple of these that are really commonly used just because they happen to be like easy to work with. Most common of these is Mcpda, which looks like, you don't have to be able to draw this from scratch, but you should recognize when you see it that this is a peroxy acid functional group on the molecule. Okay, so this is M, so you might see it with or without a hyphen, but the M is lowercase. All the other letters are capitals. I've seen people swap it so it looks like Mcpda, but the M actually stands for meta. If you've taken lab, you'll remember that this is a meta-substituted aromatic ring, and then its full name is meta-chloroperoxybenzoic acid. Okay, so that's kind of beside the point. You just need to know it's got a peroxy acid group in it. Another one that's gotten more common in recent years is this one. Where it's got a negative charge on there, and then there's actually two of this thing with a magnesium +2 counterion. This is MMPP. And I think that's magnesium monoperoxyphthalate, I want to say. But again, the name's not super important. Okay. So that's actually pretty much the only thing you need to write on the arrow is just one of these. Or you might see it written as like just RCO3H on the arrow if they want to keep it pretty vague. But pretty much, it's really simple actually. It's fairly similar to how you would make a 3-membered cyclopropane ring. You start with an alkene, you bring in whatever reagents you need, say Mcpda, and you just convert it straight into an epoxide like that. You might see it written with a solvent. I think DCM is probably the most common, but there's a few other options, but you don't have to list it in there. Another example, let's try MMPP. Would just epoxidize the alkene on that molecule as well. Okay, so the mechanism for this is kind of long and complicated, so I'm going to skip that in the interest of more important stuff. I guess for our purposes, like you might see exam questions in the archives where I ask about the mechanism, but that is not fair game for us for this semester. Okay, so any questions about this stuff? Yeah, in the back.
Is there certain situations where a certain reagent is better than the other?
No, these two, or just like peroxy acids in general, are more or less interchangeable, at least on paper. In practice, you would probably want to use one of these two, which are more or less interchangeable, just because they're nice, convenient powders that behave pretty well. If you tried like a regular carboxylic acid that's smaller, say like acetic acid, the peroxy acid of that, that's just kind of a noxious, fumy liquid, so it's less fun to work with. But these are both like really easy to work with, and you guys will work with them in lab next semester too. Okay, cool. Any other questions about making epoxides by this method before we move on to the biggest chunk of what I'm going to cover today? All right, sweet. Okay. So, reactions of epoxides. Okay. So, we're going to split this into 3 different categories, but one of those is actually kind of a subset of one of the other categories, so really it's just kind of like 2 different parts and then some complications on one of those. Okay, so in all cases though, it's going to go by an SN2-like inversion on one of the carbons, whichever one gets attacked. Okay, so this is actually a lot like the bromonium ring opening that we saw in chapters 4 or 5. Where you make the bromonium ring, the 3-membered ring, and then something comes in backside, attacks one of the carbons, pops that ring open. Similar for epoxides. Okay, so first off, we're going to look at acidic conditions. Okay, so we're going to protonate the oxygen first. Then we're going to attack the more substituted carbon. This is actually the closest analogy to bromonium ring opening from before. Okay, so maybe let's do the mechanism first, and then look at some examples. Okay, so all right, so say this is our epoxide. We got a clear, more substituted and less substituted side of the ring. This one has one more R group coming off of it. So, what we're going to do first is, if we've got acidic conditions, we have some source of H plus floating around. I'm going to leave it vague for now, so this can be sort of generally applicable to the examples that I'll put up. But oxygen gets an H out of somewhere. Okay, so that gets us to there. And then whatever nucleophile that we have around, I'm going to leave this real vague too for now, it's going to come in and attack the more substituted carbon and pop that ring open. So this is exactly the same as bromonium ring opening. And because it's also SN2-like, okay, so this end out here on the right stays exactly the same. Nothing's changed out there. But at this end, we now have that umbrella turning inside out thing going on where these two other groups sort of get shoved up out of the way a little bit. And then nucleophile is coming down off of there. So just like any SN2, as long as the leaving group, this oxygen, has the same priority ranking as the nucleophile that's coming in, which it usually will, then this would convert this carbon from R to S or vice versa. Okay, so questions about the mechanism? Yeah. So this carbon here, like, let's see, the way I've got it drawn right now, I've got hydrogen here. I think this is going to be, this should be R right now, and I think after this reaction it's going to be S. Mm-hmm. Yeah, so it's whichever one gets backside attacked. So this carbon here did that umbrella flipping thing. Sorry? Yep, yeah, it's just because before I had one group sticking up, and now I have the new group sticking down. That flips it, stereochem. Yep. Okay, so other questions about this mechanism? Okay, cool. So let's throw some examples up here. Okay, so I'm going to draw sort of a simpler example of like a less explicit H's version of this molecule up here. If I hit this with, say, HX, like HCl or HBr, this is acting as both the proton source and the nucleophile source. So I protonate it first, and then X minus comes in and attacks. So I'm ultimately going to end up with this molecule, where the halogen here ends up attached to what used to be the more substituted carbon. Okay, another example. So a molecule, if I use ROH, so ROH can act as a nucleophile, but it's not really much of a proton source. This is not a very acidic molecule as it currently stands. So I'm going to have to throw in some better source of protons, like some sort of acid catalyst like H2SO4 to get this to go. So it's pretty much going to look similar to the last reaction there, only instead of an X, I end up with an OR hanging off of there. Okay, and then the last example is we could use water and acid as well. This is the last example I'm going to put up, but there's a bunch of other reactions that could fit into this category. As long as you've got some sort of acid source around, it's probably going to go by this, and a nucleophile, of course. Okay, so any questions about these examples? All right, one other thing I should point out is in this case, can we even tell which carbon got the new OH group coming in to attack it? We can't, right? Because like either one of these OHs could have originally been the epoxide oxygen. Either one could originally have been the nucleophile. So I'll point back at this example in just a little bit here when I compare it to base.
Wouldn't, like, because you have that double bond on one side, wouldn't you know which?
Yes, but like if I didn't know that it went for the more substituted carbon in this reaction condition, like if I just went into this blind, I'm like, okay, I've never looked at epoxides before, let's hit this thing with water and acid and see what happens. And then I'm like, well, crap, that didn't tell me much. I can't tell which oxygen went where. Unless you get fancy and start doing like isotope labeling, and maybe you have like heavy water or like a labeled oxygen water or something, and then you can like track which oxygen's which. But yeah, this reaction by itself is not as useful for tracking as like these other two would be. So, okay. Cool. So that's acidic conditions. We go for the more substituted carbon. Now let's look at basic for comparison. Basic, or in other words, nucleophilic. Well, no, let's stick with basic. Because technically both sets of reactions have nucleophiles in them. It's just these ones are more likely to be stronger. Okay, so in these cases, you don't protonate the oxygen. You're just going to go straight in for attack. On the less substituted carbon. All right, so I didn't actually look at why things happen the way they do for acid. I think I'm going to put both reactions up first and then do a comparison between them for why things happen where they do. But let me get through this one first. Okay. So you can go straight in for the attack in this case without protonating the oxygen. A lot of the times the nucleophiles that you use for this are going to be stronger than the nucleophiles up here, which makes sense, right? Like here you're kind of limited by whatever nucleophiles you have to be existing in the presence of acids, so none of them are going to be like super strongly negative charged or anything. Here you don't have protons floating around, so you can have much stronger nucleophiles. So usually stronger base nucleophiles because there's no acid around. Okay, so to do the mechanism, let's look at the same molecule again. Okay, so here we don't have any protons around. We're not going to stick one onto the oxygen. We're just going to go straight in for the attack with the nucleophile here. And for reasons I'll get into in a little bit, in this case, the nucleophile prefers to go for the less substituted carbon. Okay, so it pops the ring open, gives us an O- here. And in this particular molecule, like it still inverts the stereochemistry, but we can't actually tell afterwards because I put two H's on here, so you can't actually tell if it's R or S because it's neither. Okay, so we pop the ring open with nucleophile, kick out the oxygen, but in this case we got to do one more step to finish it up, and that is get the oxygen to be neutral afterwards by picking up a proton from somewhere else, which is usually going to be some protonated version of the nucleophile, like its conjugate acid. So we'll go pick up a proton from one of those. Which gets us to here. Okay, so you might also notice that this is sort of creating a new copy of the nucleophile, which can then go attack another thing. Okay, so any questions about the mechanism before I put up some examples and then do a comparison between the two? Yeah, sorry.
Could you ignore the stereochem on that side because it's not an asymmetric carbon?
Exactly, yep. Yeah, there's two H's, so I can get away with like not even bothering with bold and dashed. Yep. So good question. A lot of the time we'll just have the conjugate acid of it floating around already. So maybe we'll have like an alkoxide like RO- in like ROH as the solvent, that sort of thing, because that's a pretty common combination. Let's see, well, yeah, that's pretty much the only examples that I'm covering is like alkoxide in alcohol or hydroxide like OH minus in water is another way you could do that. Yep. Okay, so I'm going to take a minute, erase the other side of the board, and then we can go a little bit more into this. Okay, so a few examples of how this reaction might look might be this molecule, and we're just going to use that alkoxide in alcohol kind of combo that we've seen a few other times. So whatever OR minus and then HOR is like the solvent. Okay, so in this case, we're going to end up with OH here, and then OR stuck off the less substituted carbon. Okay, so here we can definitely tell the difference in outcome between acid and base conditions. Another option would be this, and then NaOH and H2O. So this one is not, again, something where we can tell super easily which one got attacked. I guess if we know information about the stereochemistry, then we can tell did the more substituted carbon get inverted or not, and then that would give us information about which carbon got attacked, and we can go from there. Okay, so why do these two things go different ways depending on what conditions you got? Okay, so why the difference in regiochemistry, in other words? Okay, so acidic conditions, it all comes down to the positive charge. So we could describe this as acidic conditions are under electronic control. The outcome is dictated by charge distribution primarily. And again, this is exactly what we saw for bromonium ring opening in chapter 5. So if you have like a positive charge on that ring there, Remember, just like for bromonium, you're going to have a little bit of charge distribution pulling towards it from the two carbons, but this one is going to have a pretty small delta positive just because it's not really great at helping out that oxygen. It doesn't have much stabilization. It can't really carry much of a positive charge because it's less substituted. This one here has a much bigger delta positive. So bigger delta positive means that when the attack happens, when it's got to attack one or the other of the two carbons, the attack's going to happen there. That's okay. All right, so that's kind of what's going on with positive charged ring. Basic conditions don't have that. So what's going on here? Turns out the only factor that leads us to pick one or the other is sterics. So basic conditions are under steric control. So there it's just like which side is more attackable for SN2. So here, if we have this molecule, this one with the extra methyl is going to be harder to attack than this one that just has a couple extra H's. Okay, so just by having an extra proton on there or not, which dictates whether we have a positive charge on the ring or not, that can just totally flip the outcome of the reaction and also totally flip like what effects ends up being the most important for determining the outcome of the reaction, which is pretty cool. Now we can pick and choose which carbon of the epoxide we attack just based on which conditions we expose it to. Kind of like how we can pick Zaitsev versus anti-Zaitsev or Markovnikov versus anti-Markovnikov. Okay, so questions about those two. Okay, cool. So the third category that I'm going to get into is probably the most long-term useful out of all of these, but it's a subset of basic conditions. And this is specifically using a very strong base, which is an organometallic. Okay, so we would kind of expect, we know organometallics like R attached to lithium or magnesium are very strongly basic. So I'm going to deliberately put up a simpler epoxide here first, because it turns out if we hit this thing with, say, RLI, the alkyl lithium here is going to go attack one of the carbons. I made them the same in this case. So it'll pop the ring open. Stick an R on there. And then if later on we do like an H3O plus water workup, that can go protonate the oxygen, and we end up with an R attached to the epoxide, right? So that's pretty much the same thing that happened with base. The only difference is we can't obviously have H3O plus and RLI around at the same time. We already know that's not going to end well. So if we want to make sure this works on the epoxide, we got to bring it in as two separate steps. So in the arrow, we would write 1 parentheses, 2 parentheses. Okay, so that's all well and good. Overall, we would write 1 RLI, 2 H3O plus. Okay. The problem is that RLI is good in basic and it's good in nucleophilic. In fact, it's so basic that if you give it the opportunity to just rip a proton off of anywhere at all, it's going to go do that instead of this nice behaved stuff that we want. So organolithiums and are so basic that they're going to rip an H off of any carbons coming off the ring if they get a chance. Which is why I didn't put any dangly like groups coming off the ring here. Okay, so how that looks is, if I tried doing this reaction on this epoxide instead, and I'm actually going to draw this out in detail now, we might expect, given that it's basic conditions, that this is going to go for the less substituted carbon, pop the ring open just like we did up there, right? No. Instead, this is like, well, I really want an H. I'm going to go take one from over there, and that's going to kick down. So instead of doing like an SN2-like step, they actually do an E2-like step. That's how much this thing wants a proton. So you end up with double bond here, this, and R doesn't care. It's got the H that it wanted all along, and it didn't have to add to a molecule to get anything either. But that's presumably not what you were really going for when you were setting this up. Okay, so how do we get around this issue? Really what we need is some kind of organometallic that's basic but not too basic. So this is where we're going to introduce a new type of organometallic. All right, so this is called a Cuprates, or a Gilman Cuprates, or a Gilman Reagent. All right, so cuprate, that's copper. Actually, that's where the element Cu comes from. So what this looks like is you can't actually get just one copy of the R group stuck onto the copper. What you're going to do is you're going to make it from RLI. So we're going to have actually two copies of the organolithium here. And we're going to bring it together with copper in the one oxidation state, say like copper chloride, copper bromide, whatever. And then, just like always, organometallics, ether solvents, probably the best way to deal with it. THF is pretty standard. Okay, so the way it looks, the bond length came out kind of wonky in the notes for some reason, but both the bonds should be the same length. You end up actually with two copies of R stuck onto copper with a negative charge here, and then a lithium plus floating around as your counter ion. Or you could write it as R2CuLi. Okay, so this actually will add to the epoxide with no E2 nonsense going on. So if I do again, this molecule with R2CuLi, and then THF solvent or ether is fine. And then again, a water workup, then I am going to get a nice, well-behaved R group stuck on right where I want it. Okay, so questions about that reaction? Okay, so I know I only have like 4 or 5 minutes left, but this is actually pretty useful for synthesis because this is the first case that we've seen where we can actually get pretty good control over making new carbon-carbon bonds. So this is a great way to build up the skeleton of the molecule. And I apologize, but I'm not going to take the time to erase the board. I'm going to fill in this blank space I left over here. Okay, so say we're trying to make this molecule. You'll notice that when we do this reaction, the bond that we're making here, the R group that we stuck on, has R and then carbon-carbon oxygen. And then, so in other words, the R group is 2 carbons away from where the OH ended up. So we can use this to sort of work backwards. Like if we're trying to make a molecule like this one, we could say, okay, I've got oxygen, I've got carbon-carbon. So I could have brought in this methyl group as like my R group from the cuprate. So I could say do. So maybe that was my epoxide. And so I have just a methyl out there in the end. So Me2CuLi would have been a way to put that together. Just to double check, does this methyl group attack on the less substituted carbon to get there? Yes, it does. So we're good on regiochemistry. Okay, so questions about that? Okay, so that's one way to work backwards. The other way is, say for the same molecule, again, oxygen, carbon, carbon, and then whatever's left is your R group that you bring in. So I could have drawn the cut here line right there. So that would have meant that so the epoxide started out connecting these 2 carbons instead. So I start with this epoxide, and now I need an alkyl group that's adding 2 carbons at once as my cuprate. So Et2CuLi is how I could have put it together if I use that as the disconnects. Okay, so this is a pretty useful way of sticking big chunks of your molecule together. We'll see other ways in the future in OChem too, but I actually recommend working through the synthesis example at the end of this chapter, even though I didn't list it in the things to review, just because it's a good practice way of getting to use this reaction. Okay, so I'm going to wrap it up there. I'm out of time. You guys have been awesome all semester. I'll see you at the exam review session on Friday if you can make it, and if not, I'll see you at the exam.